When a sum of money is invested in an account which pays a rate of interest for a period of time, while the money is invested, the value of the money at the end of the stated period is called the future or compound value of that sum of money. This type of calculation is done when determining the attractiveness of alternative investments or when one is trying to figure out the effect of inflation on the future cost of an asset such as a car or a house. In the latter case, we use an expected annual inflation rate instead of the rate of interest in order to calculate the future cost of an asset. Now, in problems where we have one single period, such as 1 year, the future value of the sum of money would be equal to the original sum plus the amount of the interest earned over that period. So the future value is equal to the present value plus the present value times the interest rate. So let's say John deposits $200 for a year into an account that pays 6% interest for the year. At the end of the year, John will have $212. That's $200 plus $200 times 6%, which is $212. Now, if that money was left in the account for multiple periods, such as 2 years or more, then the future value of the sum of money will be equal to the original sum plus interest over the multiple periods involved plus interest earned on that interest as well. Okay, so and in that case, the future value is equal to the present value times 1 plus the interest to the nth power, or the number of periods. So if John closes out that account after 3 years, how much money will he have accumulated? How much of it would be interest on interest? And what about if we had it in that account for 10 years? So at 3 years, it would be the $200 times 1.06, the interest to the third power. So that would be $200 times 1.191016, which is $238.20. Now, the interest for the 3 years is $36, and the interest on the interest is $2.20. Now, if we had it in that account for 10 years, then it'll be $200 times 1.06 to the 10th power, or $200 times 1.790847, which is equal to $358.17. Now the interest, the 6% interest for the 10 years is $200 times 0.06 times 10. That's $120. But the interest on the interest is now $38.17. So when you have it in the bank, your interest is earning interest as well. So let's say you know how much money you will have accumulated in the bank after 4 years if you deposit all $500 of your graduation gift into the account, which pays interest of 5% a year, and you leave it untouched for all of the 4 years of college. What would that amount be? What is the present value of that $5,000? I'm sorry, what is the future value of that $5,000? So the future value would be your present value times the present value times 1 plus the interest rate to the nth power. Now, we can do this manually, or we can use a calculator, or we can use a spreadsheet, right? And in this case, the reality is many of us will use either a calculator or a spreadsheet. So in that case, the present value is the $5,000. The rate is 5%, and N stands for the number of periods. and in this case, 4 years. So if I was to use that in a calculator, then I would put in present value, 5,000, N would equal 4, and I would equal 5. And my payment, which is PMT, will equal 0. And that would give me $6,077.50. If I was using the Excel spreadsheet and I wanted to know the present value, I would search the formula present value, and I would use the following factors. I would use present value as 500, and I would use the rate as 5%, and the number of periods as 4. And that would calculate to $6,077.53. Now, calculating the present value of a single sum of money that will be received after a number of periods involves discounting the amount of interest that would have been earned over the period of time at the given rate of interest. It is therefore the exact opposite or the inverse of calculating the future value of money. So such a calculation is useful for determining today's price or the value of an asset or the cash flows that will be received in the future. So basically what we want to know is if I had this money over time, or if I had this money in 5 years, what would that money be worth to me today? So let's say you won $50,000 at the casino and you'd like to save a portion of it so that you have $40,000 to put down in the house after 5 years. The bank is going to pay you 6% interest on that money. How much money do you need to set aside in order to have of those winnings? So we know the future value is $40,000, right? That's the down payment we want. And we know the number of periods is 5, and we know the interest rate is 6%. So we can solve for that using our calculator, or we can solve for that using our spreadsheet. Our rate would be, we're solving for present value, so we would search for the present value, and we would use the rate as 5%. I'm sorry, 6%. The number of periods is 5. The payment is 0. And the future value is $40,000. And that would give me my present value. So that present value would be equivalent to $29,890.33. So basically what we're saying is if we want $40,000 in the future, we need to put in the bank today $29,890.33. So often we're faced with financial situations that involves equal periodic outflows and inflows of cash. Such payment streams are known as annuities. Examples of annuity streams include rent, leases, mortgages, car loans, and retirement annuity payments. An annuity stream can begin at the start of each period, as true for rent or insurance payment, or at the end of each period, as the case with a mortgage or loan payments. Okay, the former type is called an annuity due, and the latter is known as a ordinary annuity stream. So although future values of ordinary annuity streams can be calculated using the same process as the future value, there's a simplified formula that you can use to make it easier, okay? And you can calculate this using your spreadsheet. You can use your calculator, or you can do your formula. So the future value is equal to the number of payments the payment amount times 1 plus the rate to the nth power minus 1 divided by the rate. And I know I said a lot. That's the payment times 1 plus the rate to the nth power, the number of periods, minus 1, and that will be all divided by the rate. So let's say Jill has been faithfully depositing $2,000 at the end of each year uh, for the past 10 years into her bank account that pays 8% interest per year. So how much will she have accumulated in her account? All right, so we can do this a long way and find the present value of the first payment, and then the present value of the second payment, and then the present value of the third payment. We can do that, and then we can sum them all up. Or we can use our calculator or our Excel spreadsheet, and we have the information we need. We know that the number of periods, how many years, 10 years. We know what her payment amount is, $2,000. We know the interest rate, 8%. And what we want to know is the future value. So we would use the future value formula, and we would enter that information. So again, rate 8%, number of periods 10, payment amount is $2,000. You should get a future value of $28,973.13. So if we're interested in finding the value of a series of equal periodic cash flows that are at the current point of time, we can sum them up using the discounted values of each periodic cash flow payment related to that period. So if I wanted the present value, then it would be equal to that payment times 1 minus 1 over 1 plus the rate to the nth power, all divided by the rate. We can do this manually, or we can use our calculator and our Excel spreadsheet. So let's look at an example. John wants to make sure that he saved up enough money prior to the year before which his daughter begins college. So based on current estimates, he figures that college expenses will be about $40,000 per year for 4 years. And that does not include any inflation or tuition increases during the 4 years. So how much money will John need to have accumulated in the account that earns 7% per year just prior to the year that his daughter starts college? So he wants to know how much money does he need to have now to meet those 4-year needs. So we know that the number of years is 4. We know his payments is $40,000 per year, and the rate is 7%. So if we wanted the present value of that amount, that $160,000, because that's roughly what it is, $160,000. I'm sorry, can't add. Yeah, $160,000. So what is that equivalent to if we had that money today? So we're solving for the present value. Again, we can use our calculator or we can use our Excel spreadsheet. We have the relevant information. We have the number of periods. So we would plug this into either our formula in our calculator or our spreadsheet. The rate, 7%. The payment, $40,000. The number of periods, 4 years. So that is equivalent to $135,488.45 today. Now let's talk about loans for a little bit. There are 3 loan payment methods that we use. And then depending on the terms agreed upon at the time of the issue, the borrower can typically pay off the loans one of 3 ways. They can pay off the principal, which is the original loan amount that you borrowed, and all of the interest, the amount that the lender charges you to borrow your money at one time at the maturity date of the loan. That would be what we call a discount loan. So you're going to make one lump sum payment at the end. You can make periodic interest payments and then pay the principal and the final interest payment at the maturity date, and this is called an interest-only loan. This is typically how bonds work. And then you can pay the principal and the interest as they go by making equal payments each period, and this is called an amortized loan. So this is typically the way we may make our car payments and our mortgage payments. So let's see. Roseanne wants to borrow $40,000 for 5 years. The lender offers her a choice of the 3 payment structures. She could pay all of the interest, 10% per year, and the principal in one lump sum payment in 5 years. She could pay the interest of 10% per year for the first 4 years, and in the final year she pays the principal, the last interest payment, and then the money back. Or she can make 5 equal payments at the end of each year, which would be inclusive of interest and the principal. So what we want to do is we want to analyze those options that are available to Roseanne and help her determine which one is the better rate or the better loan for her. So using the discount method, where we're going to make the one lump sum payment in the end, we're going to simply use the present value method to determine this. So since all of the interest and the principal are paid at the end of the 5 years, we use the present value of a lump sum equation to calculate the payment required. So what is it? The future value plus 1 times the rate to the nth power. So the future value, the present value, $40,000 times 1 plus the rate 10% to the 5th power, or 40,000 times 1.61051, that equals to $64,420.40. So we're paying one payment of the principal, $40,000, plus the interest, $24,420.40, for a total of $64,420.40. Now, if we were going to do the interest-only loan, then we have to determine what the interest rate is for periods 1 through 4, right? And then in the 5th year, we would calculate the interest for that period plus the principal payment. So the interest for periods 1 through 4 is $44,000. 40,000 times 10% is $4,000. So years 1, 2, 3, and 4, you are going to pay $4,000 in interest. In year 5, you're going to pay $44,000. The $4,000 of interest and the $40,000 principal payment. So total, you've paid $60,000. $20,000 in interest and $40,000 of the principal back. And then lastly, we have the amortized loan, which most of us are pretty familiar with. To calculate the annual payment of principal and interest, we have to use the present value of an ordinary annuity and solve for the payment using the following information. So we can do this in our calculators or as well as in Excel. We have our number of periods, which is 5, the number of years. We have our interest rate, which is 10%, and we have our present value, which is $40,000, and our future value is 0. And this will give us our payment amount. Okay. So if we were to enter that information into the system, our payment amount, our equal payment amount would be $12,759.50. So our total payments would be our payment is $10,551.89. So our 5 payments, equal payments, would be 5 times $10,551.90. That totals $52,759.50. So in this case, your total interest paid is $12,759.50. So if I'm doing the discounted loan, I am going to pay most. So we don't want to recommend to Roseanne to do the discounted loan because she's paying $24,420.40. The interest only loan is $20,000, but the amortized loan is $12,559.50. And the reason being is that you're only paying interest on the principal. In the other 2 loans, the principal remains $40,000 for the duration of the loan. However, in the amortized loan, the principal amount is declining over time because you're making a payment that is including a payment back to the principal as well as to the interest. Now, the annual percentage rate, or the APR, is the most commonly quoted interest rate for most loans and fixed income instruments. However, unless interest is charged only once per year, the annual percentage rate will understate the true cost of interest to the borrower. Now, very often, lenders charge interest more often than once for the year. For example, once a month. So in that case, the APR is divided by the number of compounding periods per year. So to calculate the periodic interest rate, so if we have an APR of 12% compounded monthly, then the periodic interest rate is 12% divided by 12%, which is equal to, 12% divided by 12, because it's each month, which is equal to 1%. So an increase in the frequency of the compounding leads to a reduction in the periodic interest rate, but to the increase of the effective annual rate. Now, since the interest earned in each period is also earning interest over the subsequent periods. So the effective annual rate is the true rate of return to the lender and the true cost of borrowing to the borrower. So an effective annual rate is also known as the annual percentage yield on the investment, and it is calculated for any given APR and frequency of the compounding by using the following equation, which is 1 plus the APR divided by the months to the number of months minus 1. So let's look at this. The First Common Bank has advertised one of its loans offering the following. We will lend you $100,000 for up to 3 years at an APR of 8.5%. That's the interest compounded monthly. If you borrow $100,000 for 1 year, how much interest will you have paid the bank? And how much interest will you pay, and what is the bank's yield? Well, the nominal rate is the APR of 8.5%. The frequency in the compounding is 12. And the periodic interest rate then would be the APR, the 8.5%, divided by the number of months, 12. And that's a rate of 0.70833. So the actual earning is that 1.0070833 to the 12th power minus 1, which is 1.08839 minus 1. So the actual interest rate that you would be paying is 8.839. So while they are advertising 8.5%, what you are actually paying is 8.839% because of the compounding, because they are charging interest every month. So the interest paid would be 8.839 times the $100,000 for that year. You would pay $8,839.09 of interest. So lastly, the rate of interest earned on a risk-free investment such as a CD bank or a treasury security is essential to the compensation paid for giving up the current compensation by the investor and is known as the nominal interest rate. However, inflation can erode the purchasing power of money, and therefore the true reward of waiting is often expressed as the real rate of interest earned and the rate that remains after inflation has been adjusted for. So we use the Fisher effect, uh, that equation, to show the relationship between the real rate and the inflation rate and the nominal rate. Whereas the real 1 plus the real rate is equal to 1 plus the real rate times 1 plus the inflation rate. So the nominal rate is equal to 1 plus the real rate times 1 plus the inflation rate minus 1. Or the nominal interest rate is equal to the real rate plus the inflation rate plus the real rate times the inflation rate. So let's look at this. If the real rate is 3% and the inflation rate is 4%, then the nominal rate would be 3% plus 4% plus 3% times 4% for a rate of 7.12%. So let's say Jill has $100 and if she's tempted to buy 10 t-shirts, which is going to cost her $10 each. However, she realizes that if she saves the money in the bank account, she would be able to buy one more t-shirt, so she'll be able to buy 11 t-shirts. Now, if the cost of the t-shirt increases by the rate of inflation, which is 4%, how much would her nominal and real rates of interest have to be? Well, the real rate, which is the reward of waiting, is equal to the present value divided by, the future value divided by the present value, to 1 divided by the number of periods minus 1. So 10 shirts divided by 11 shirts, we wait divided by to the 1 over 1, which is to the nth power minus 1. So that real rate of interest is 10%. So now the price of the t-shirts for the next year would be the $10 times the inflation rate of 4%. So it would be $10.40. So the cost of the 11 t-shirts now is $10.40 times those 11 t-shirts would be $114.40 if she waits. So the present value of, so the nominal rate would be equal to 14.4%. The real rate plus the inflation rate plus the real rate of interest times the inflation rate. So the real rate is 10%, plus the inflation rate of 4% plus 10 times 4%, which would give you the nominal real rate of 14.4%.